last one. So it's a sweet ending for this one. We're at the dessert phase of a very long meal. So thank you everyone for sticking with us. And just looking at the numbers, they're going up and down. People are dropping in, disappearing, dropping in. And that's exactly what we wanted. And remember, we'll have the recordings available after the event anyway. So the final presentation for today is dealing with kiwifruit. And in fact, is around predicting kiwifruit count and size from harvest and climate data. The project, led by Dr Jianlong Zhou from the University of Technology, Sydney, and Dr Evan Webster from the Yield Technology Solution, involves teams from both organisations. And Zespri, a major kiwifruit producer in New Zealand. So the presentation will be delivered by lead researchers, Dr Jianlong Zhou and Dr Zhidong Li, both from the University of Technology, Sydney. The project exists to create accurate annual crop estimates of Zespri's supply chain. And this will have a major impact on the productivity and profitability of this particular organisation and the industry more broadly. So welcome Jianlong and Zhidong. I look forward to hearing from you.
Thank you for David's introduction, and good afternoon, everyone. My topic today is predicting kiwifruit yield and size. This is a collaborative project with Yield, Zespri, and Agriculture Risk Management in New Zealand. Zespri is the world's largest kiwi exporter in New Zealand, and ARM provides bespoke, independent solutions to the horticulture industry in the areas of insurance, research, compliance auditing, and orchard assessment. The Yield is an Australian agriculture technology company to transform food and farming practices by digital technology. In this project, Zespri and ARM provide kiwi yield data in New Zealand to UTS and the Yield. And UTS is developing data-driven approaches to accurately predict kiwi yield and size. The outcomes are then delivered to end users through the Yield's digital platform. This is our research team from UTS, the Yield, Zespri, ARM, and Food Agility CRC. Before the project details, let me first introduce our Data Science Institute. And the UTS Data Science Institute is a collaborative impact-focused data science group. We deliver data science solutions to industry and a wider community for the real-world impact. We have a big group of researchers and engineers in areas of machine learning, software engineering, data engineering, visualization, and cloud deployment. We are doing cutting-edge research in data science and AI, and we also have extensive engagement with industry partners that have delivered different projects for real-world impacts. So what we are doing in our institute, we are working across the full data science delivery life cycle, from opportunity discovery, data preparation, data analytics, predictive analytics, optimization, data-driven operations, insight presentation to business and solution integration. And we are working on problems from different aspects and have delivered data-driven solutions in a diverse range of sectors, such as transport, energy, health, retail, agriculture, and also others. It's a little small. DSI, our institute has a wide range of techniques and tools that can be used to solve different problems. For example, computer vision, including object detection and semantic segmentation, pose detection and key point analysis approaches, regression and machine learning for prediction tasks, cluster array to automatically identify different groups, factor analysis to identify critical characteristics or data elements, natural language processing to extract knowledge from text. And we are also doing multi-objective optimization to find the optimal set of trade-off solutions, and also interesting like outlier and anomaly detection to identify typical, unusual, or exceptional groups and behaviors. And here are some of our typical projects we have done. For example, transport projects on predicting traffic delays and propagation of delays, AI ethics project on identifying and managing ethics risks in HR decision-making, finance project on automated data-driven quality assurance systems for underwriting and socially responsible investment, and also water project on forecasting water pipe failure and risks, health project on prediction of drug side effects, optimal medical imaging or automated illness identification and others. And here is our like water project we did before. In the water project, we have done extensive foundational research in machine learning and data analytics. This is a like application-focused research for different water pipe related problem solving with data-driven solutions. And we have partnered with more than 30 global water utilities, including Australian major water utilities. And the project has significant academic impact with papers in top journals and conferences. And the project also has big industry impact and value with a large amount of economic benefits. And the work has been recognized by also the industry and academy with different awards. Yeah. Now let's have a look at the background of our Kiwi project. We know that Australia and New Zealand are significant water producers of many agricultural products. For example, according to Australia's Department of Agriculture, agriculture accounted for 11% of merchandise exports compared to 5.9% of GDP in 2019 to 2020. And fruit is one of the top 10 export agriculture products in value together with cattle, crops, sheep, wine, dairy, wool, and sugar in 2019 to 2020. And the value of Australian fruit exports has been increased sharply in the right diagram in recent years. New Zealand also has a similar exports. And more specifically, New Zealand is the world's largest exporter in Kiwifruit. As shown in the left figure, the produce from New Zealand, the horticulture industry is more than $10 billion in 2020, while Kiwifruit is the exported fruit with the largest value in 2020, followed by wine, apples, yeah, as shown in this right diagram. And also in New Zealand, Raspberry is the largest kiwifruit exporter. Here are some statistic information on kiwifruit sold by Raspberry in the past years. For example, toad sold or trays sold in each season, yield area planted at orchard gate returns are almost gradually increased through years. And the right diagram shows the raspberries production profile in the past years. For kiwi fruit, the kiwi fruit can be categorized according to its varieties and growing methods. For varieties, we have green and gold kiwi, while growing methods include conventional and organic. Therefore, we can have 4 categories of kiwi. Green kiwi with conventional and organic, and gold kiwi with conventional and also organic, 4 categories. The kiwi fruit growing season in New Zealand begins from June until May of next year. In June to August, the winter chill and other weather factors affect the yield of kiwi. In September to November, flowering begins for kiwi growing. Yeah, in this period, this is the flowering period, and December to February is a quickly growing time of kiwi fruit, and March to May is a harvest time, and finally kiwi fruit is packed for selling. And this is a typical kiwi trading process. In this process, exporters set up market access plans in February, and then they negotiate supply and price contracts with buyers in March. Contracts are finalized and adjusted in April before the harvest time, and finally logistics are planned for trading. And in the kiwi industry, export plays an important role in linking grower and also marketed consumers. Exporter usually estimates the kiwi yield from growers based on the yield, they sign contract with other companies and then plan logistics for the final market and customers. In this process, accurate estimated kiwi yield plays an important role for the exporter to realize their price plan. If the estimated kiwi yield is too high than the actual, exporter has to buy additional kiwi from others to meet their contract. If the estimated kiwi yield is too low than the actual, it is a waste for the exporter. Therefore, such uncertainty in the yield means the loss of sales opportunities. And it is estimated that uncertainty in yield costs around $20 million per year in New Zealand, the kiwi industry. So in this case, we proposed data-driven approaches to accurately predict kiwi yield to support the exporters contracting. Like before exporter sign the contract, we provide we accurately predict the yields to exporter, and then exporter can sign contract based on this prediction. In this kiwi yield prediction, we can use different data sets related to kiwi to train machine learning models and predict the yield. This is a process. Like we have data, different data, visual expression, historical data, weather data, and this data, and then we set up the model and then predict the yield. And these data, typical data we are currently using in our work. One is weather data, measurement and operations data, historic data, remote sensing data is a potential data to be used. And the main challenges we meet in kiwi yield prediction include include two aspects. One is to convert domain knowledge into features used in machine learning. This is because that domain knowledge on kiwi growing is usually abstract and very complex, and the digitalization of such knowledge for machine learning is often a challenge. And another challenging aspect is to predict kiwi yield accurately using short period of data sets. In our study, we have a short period of historical data for model building. We only have 8 years of historical data, and each year has a 1 year record for each orchard. It is a challenge to build accurate prediction with such a short period of data. And then how to deal with these challenges? Here, I give some practices in our work for these challenges. We have different workshops. We had different workshops with Zespri and ARM to understand how different weather factors affect the kiwi yield. From the workshops, we identified weather factors such as wind chill, sunny days, daily rain frequency, and others. And according to the definition of these factors, we defined different features based on the collected weather data. For example, winter chill is defined as accumulated hours on the 7 degrees in weather data. And sunny days is defined as the mean sunshine hours per day, according to the weather data, and also other features. Yeah. And in order to mitigate the challenge of high accurate model building with a short period of historical data, we used a boosting approach based on the random forest. For example, we first randomly sample the dataset and then sample features randomly for the selected data, and then a tree-based model is then built to predict the yield. And after repeating a series of such processes, the prediction results from these processes are aggregated to get the final result or final prediction. And finally, this is our conclusion. In our work, domain knowledge has been successfully digitalized based on the weather data, and we also use the boosting approach for the prediction with short period data, and the yield model has been built successfully to accurately predict the yield of kiwi. And our future work will be the kiwi size prediction and also to integrate yield and size prediction together. And because we consider the data privacy concerns from our industry partners, we didn't include much details on data and also prediction outputs. Yeah, that's all for our project introduction. Thank you.
Thank you, Jianlong and Zhidong. And this project brings in the if you like, that other dimension we heard earlier today. The statistical and mixed models for forecasting key development stages to feed into a supply chain. Dan, of course, and Darren, through their projects, talked about machine learning, and this is another machine learning based approach. You focused again on climate variables as an input into the model. What about the other potential constraints to growth and development of the crop, such as soils, fertility, that sort of deal? How does the model deal with the non-climate variables or factor in the variability that not having them may bring in?
Yeah, we have different weather features we just mentioned, and we hope we can have other like management features such as soil or fertilizer, those kind of features. But we currently don't have those features, and that's the main constraint for us to improve like prediction performance.
Yeah, and let me just add something else.
Yeah.
Yes, as Jianlong mentioned, we don't have those data. Well, hopefully we can get some those things, and also in the operations in the different orchards, they will be very different during past 8 years. One thing we can do at this moment is using some techniques of grouping. Like usually we can't see those things. We can't see those things. We can imagine, but we can imagine that some orchard they have a similar soil type, and they have similar operational strategies or some similar devices or equipments to do that. So this kind of a thing give us some hint, which is latent, but we can infer them from the final productivity levels. So we do such grouping, and we can see from different things something like not only the total productivity trace, but we also can look into the yield rate, like how many trays per hectare, something like that. So we can see the similar patterns of different orchards through these 8 years or recent 5 years. In that case, those orchards can be grouped into the same cluster, and we can see the learning different isolated model or dedicated model for that subgroup.
Yeah, it strikes me as a particular desirable functionality that the machine learning approach brings. So, Jianlong and Jianlong, would you like to share with us any particular eureka moments, any watershed moments that really helped you crack the nut of getting this project up and running?
Zhou, please.
Yeah, okay, no problem. So this kind of eureka moment, for my understanding, we have two major challenges. One is that we don't get the whole data. As I mentioned, we don't have the soil data or those things. We only focus on the weather data at this moment, and also that's not the only data shortage challenge. We also have something like you can see we have 8 years of production. We have 8 years of productivity data. So if we consider the whole the Kiwifruit productivity as the whole number, then we only have 8 numbers. But we can, so to solve this problem, we have divided those productive numbers into different orchards. Like I mentioned, just then we use some grouping activities, and we find out the different very different productivity patterns through these orchards. That's one thing we have discovered. They have very even for the same category, they have a very different productive patterns. Mentioning that they may employ some new technology, maybe just I guess, but you can see that the change of the yield rate for those individual orchards. Yeah, and then the other thing is we did develop some method that we haven't finished yet, but it looks that in this at this moment it looks that the methods are useful, and that method can increase the data volume we have. That we have 8 years. So for those 8 years, it will be considered a very short time series problem. But actually we did some data embedding techniques to increase those 8 years data into a high into more granular into data with finer granularity. In that case, we have longer time series. You can consider we interpreted kind of interpret the gaps between these 8 years, and we get more data to fit into our model. So that's also that prevent the model from kind of overfitting problem as we have more data. Then we can employ some more complex model or more powerful model to the problem.
That's another dollar. That's a really interesting pathway you're exploring. So really looking forward to hearing about the tactics you bring to bear to richen up the data. And just to take that one step further, I've got a question here. If there was another piece of data that you could reach for, what would you consider would be the next important piece of data that you love to have if it was available to help your model along?
Yeah, I think the most important data could be, as you just mentioned, like fertilizer or soil data, or more granular, like management data for kiwi. For example, counting flower numbers, and also like some manual check during the growing period, and those data can like give us some reference for model building.
Yeah, so that's particularly insightful, because really what we're saying here in general, and it's a common thread we've heard today, is that, you know, data everywhere, but doesn't help us sort of think. If I can drive that Samuel Taylor Coleridge poem a bit harder than it used to be. The point is that if we want to create value from data, we have to put more work into generating data that matters. And so it's not a shortcut for industry. Get out there and collect your soil data, collect your observation data as your crops develop. So that's really insightful. Can I ask you then, what would you feel is the hardest challenge that you've had across your project, be it technical or dealing with industry? What advice do you have to give to our friends in our family here about the most gnarliest problem in your project?
Yeah, I think the first thing is because this is a data science project, and the most important for us is data available for us. And the hardest thing is to get the complete data as we expect for model building. Usually, we cannot get enough data for model building, so we have to use different techniques to mitigate this problem.
Yes.
Yeah, it's kind of we can get you can imagine we have a large area of this to be predicted, but we can only get data for certain sub-regions of that we can't know the whole general situations for the whole region. So that's kind of a challenge, and I think it's a part half to half, because this is a very big region that must include many orchards to incorporate many orchards into this data contribution problem. So not everyone will contribute the data, and also the data quality is not like unified standard, but we can still get I can say more than half of them, and that for that part of those region we can do the prediction. But for the other part of the region, if they can give us the data, and then we can put it into our model to enforce our model. Yeah.
Excellent, thank you. Jianlong and Jianlong, thank you both, and to your wider team for your contributions today. It's a very insightful presentation. Thank you indeed.
Thank you.
Thank you.